Section 1.8, inverse functions. So our objective for this section is to verify inverse functions, find the inverse of a function, use the horizontal line test to determine if a function has an inverse function, use the graph of a one-to-one function to graph its inverse, and to find inverses of a function and graph both functions on the same axes. Okay. So what we're going to need to do in this section is previous sections, we've added functions, subtracted, multiplied, divide, and made combination functions and composite functions. In this section, we're going to examine a new relationship, and that is that of a function and its inverse. Okay, so if we look at two functions that describe situations relating to the price of a computer. So in my first function, I'm going to take $300 away from the computer's price. In the second function, I'm going to add $300 to the computer's price. And you can probably see when you think about this, well, if you take $300 away and then you add $300 later, you're pretty much going back to where you started. The one function is undoing everything that the first function did. And that is the relationship of a function and its inverse. Let's kind of see how this works. So function f subtracts 300 from the computer's price, and function g adds $300 to the computer price. Let's see what f of g of x does. So we're going to put g of x into f. And when I do that, I replace x with g of x with g of x, which is equal to x plus 300. Notice that we get right back to the beginning. We get to the original computer price, just x. Okay. So using f of x is equal to x minus 300 and g of x is equal to x plus 300, we see that f of g of x is equal to x. By putting g of x into f and finding f of g of x, the computer's price x went through two changes. First an increase, the second a decrease. So first we added 300 and then we subtracted 300 to get the final price of the computer, x, to be identical to its starting price. So in general, if the changes made to x by a function g are undone by the changes made by a function f, then f of g of x is equal to x, and also g of f of x is equal to x. And this undoing, taking everything that your first function did and going back the other way, is the properties of something called an inverse function. So under these conditions, we can say that each function is the inverse function of the other. The fact that g is the inverse of f is expressed by renaming g as f inverse. Now, that is a negative exponent, which is equal to 1 over x. That is not what this is right here. That little negative 1 is not an exponent. Looks like an exponent, but it's not. It's just notation. Okay? So what we're really doing is we're saying that f and g are related to each other. That f of x and g of x are really f of x and f inverse of x. If I have these two functions, one of them undoes the other one. And that's all that notation says. So don't get confused that this is some sort of exponent and we're going to have to do some weird fractions and things like that. We'll have some fractions, but not because of that inverse sign. Okay? So let's look at this with numbers. So we can use partial tables of coordinates for f and f inverse to gain numerical insight into the relationship between a function and its inverse function. So when we look at these two, we can see that x's, inputs that go into my original function, go down by 300, and inputs that go into my inverse function go up by 300. And hopefully you notice that this column is the same as this column. This column is the same as this column. So x's turn into outputs in my inverse, and outputs turn into inputs in my inverse as well. And we can illustrate the fact that the set of ordered pairs, x comma y, in my original function, turn into similar ordered pairs, but just y comma x. X's and y's switch. This is going to be a big part of how we connect inverses to each other. So with all this in mind, the formal definition of an inverse function is let f and g be two functions such that f of g of x is equal to x for every x in the domain of g, and, meaning they both have to be true, g of f of x is equal to x for every x in the domain of f. And the function g is the inverse function of the function f, and denoted by my f inverse symbol. Thus, right, if I plug one function inside the other one, these two things happen. Okay, only now I can change the name of g to f inverse. So the same thing is going to happen, that f of f inverse of x is equal to x, and f inverse of f of x is also equal to x. And here's really important. The domain of f is equal to the range of the inverse, and the range of f is equal to the domain of the inverse, because of this property right here, that x's and y's are going to switch places between the function and its inverse function. And again, that's something that we're going to use in a few minutes. So first, let's verify inverse functions. To show that f and g are inverses of each other, we have to show that f of g of x is equal to x, and that g of f of x is equal to x. If this is true, then we can know that these two things are inverses of each other. So let's start with f of g of x, and then we'll do g of f of x. So for f of g of x, I take g and plug it into f. So this turns into 3 times x minus 2 over 3 plus 2. Well, if I follow order of operations, I multiply the 3 times x minus 2 over 3. Those two cancel. And I get x minus 2 plus 2, which is x. That's good. That worked out. But I also have to check the second one. So g of f of x must also be equal to x. And so now I plug f into g. So I take 3x plus 2 minus 2 over 3, which is just going to be 3x over 3, which is x. So both of these, when I plug them into each other, are equal to x. So these two functions are inverses of each other, and I can rename g f inverse of x, because these two functions are now related. That one undoes all the changes by the other one. And you can kind of see that happening, because in this first function, we're going to multiply by 3 and then add 2. In the second function, we're going to subtract 2 and then divide by 3. Okay, so we're just going in one function, we're going forwards, and the other function, we're going backwards. All right? So the definition of an inverse function tells us that the domain of f is equal to the range of the inverse, and vice versa. This means that if the function f is the set of ordered pairs x, y, then the inverse function f is the set of pairs y, x. If a function is defined by an equation, we can obtain the equation for the inverse by interchanging the role of x and y in the equation for the function of f. So our first example, we have two functions. We have f of x, we have g of x, which we're showing is the inverse. What we're talking about now is actually finding the inverse when I just have one equation. So to find the inverse of a function, we're going to follow these 4 steps. First, replace f of x with y in the equation for f of x. So just going to make f of x, y. Interchange x and y. And I can do this because of the property that says the domain of f is equal to the range of the inverse. So I can change x and y. Once I do this, I solve for y. If the equation does not define y as a function of x, then the function f does not have an inverse function and the procedure ends. And it is possible for a function not to have an inverse function. Okay? It still could have an inverse, but that inverse does not have to be a function. And we'll see a couple of them that don't have inverse functions. If this equation does define y as a function of x, the function f has an inverse function. And if f has an inverse function, we replace y with f inverse to show that these two functions are related and they're inverses of each other. And then if we want, we can verify our results by showing that f of f inverse of x is equal to x and the f inverse of f of x is also equal to x. This procedure for finding a function's inverse uses something called the switch and solve strategy. Switch x and y, solve for y. Okay, so if you can't remember every step, those are the two most important. Switch x and y, solve for y. Okay. Let's try to find the inverse of some functions. Okay, so step one, replace f of x with y. So we have y is equal to 7x minus 5. Step two, switch x and y. So now I have x is equal to 7y minus 5. Notice I didn't move any of the numbers. I'm not adding anything to both sides. All I'm doing is taking the y, switching it to the letter x, taking the x, switching it to a letter y. Okay? So step three is to solve. So we start with our equation. I'm going to add 5 to both sides to give me x plus 5 is equal to 7y, and divide out the 7. Okay? So now, when I look at this, let me write my function again. So we have y is equal to x plus 5 over 7. So step 4 is going to be replace y with the f inverse of x if it is a function, which it is. So we put f inverse of x is equal to x plus 5 over 7. And all I'm doing here in this last step is showing that this function and this function have this special relationship that they undo each other. If I want to prove it, I could plug this one back in to the original function and the 7's would cancel, the 5's would cancel, and I'd be left with just x. Okay. Let's try another one. Now we have a cubic function. So step 1 remains the same. Instead of f of x, write y. So y is equal to x to the third plus 1. Step 2, switch x and y. Everything else stays exactly where it is, including the exponent. Okay. Step 3 is solve. So we have x is equal to y to the third plus 1. Subtract 1 from both sides. And now, in order to get y by itself, we take the cube root of both sides, which leaves me with, as I flip this around, y is equal to the cube root of x minus 1. And step 4 would be to write it as an inverse, to write y as f inverse of x, because the cube root of x minus 1 is a function. So the function and this new thing that I created are inverses of each other. Let's try a couple that are a little more complicated. So step 1, y is equal to 5 over x plus 4. Step 2, switch x and y. So x is equal to 5 over y plus 4. Okay. Now I got to solve. So to solve this, y plus 4, I'm going to subtract 4 from both sides. And I get x minus 4 is equal to 5 over y. And now from here, I want to get y by itself, but the most efficient way to do that is to get it into the numerator. So I'm going to multiply both sides of this equation by y. And when I do that, I get y times x minus 4 is equal to 5. Now I could distribute, and I could do other weird things like, um, no, I could just try to distribute, but there's an easier way. And that's now I have multiplication. Just divide the x minus 4 out. Those cancel, and my new function is y is equal to 5 over x minus 4. And step 4, this is a function. So these two functions are inverses of each other. Okay. Let's try one more on this page that's slightly more complicated. Same idea. Oh, and up in here, right, we can see in this first equation that x cannot be equal to 0. And in this last one, x cannot be equal to 4. Well, all that means is that we can't have 0 in the denominator, so nothing to get too crazy about here. But you'll notice that these two are different, and you'll never get y to be equal to 4 in the original equation, and you'll never get y to be equal to 0 in the second equation, because if we switch x and y, when we do that, if we kept the restriction here, x is not equal to 0, when I switch x and y cannot be equal to 0 here. So the domain switches to the range, and the range switches to the domain. And that's all that this one includes as well, but we don't have to go too crazy about it. The harder part is to get y by itself. All right, so my first function, or my first step, is to write y instead of f of x over 7x plus 6. My second step is to switch x and y. So I have x is equal to 2y plus 5 over 7y plus 6. Okay, let's jump right into step 3, which is solving. And to solve this, the best way that I can think of, and let me write this with a little bit more room, 2y plus 5 over 7y plus 6, is to clear the denominator. So to multiply both sides by 7y plus 6. And when I do that, these two cancel out, and I'm left with 7y plus 6 times x is equal to 2y plus 5. Now, in the previous question, I didn't have to distribute because once I got to this step, once I multiplied both sides by y, I only had one y that I was trying to get by itself. Here I have two, one there, one there. So the only way to tackle this one is to distribute that x. So we have 7xy plus 6x is equal to 2y plus 5. And now to get all these y's together, I'm going to put them on the same side. 7xy and 2y are not like terms, but I can still subtract it from both sides and get 7xy minus 2y. I'm also going to subtract the 6x from both sides to give me 5. Let's write this first. Negative 6x plus 5. Now, because of both of these terms on the left have a y, I can factor it out. And now we can see, hopefully, my last step is now to divide out the 7x minus 2. So my function now looks like y is equal to negative 6x plus 5 over 7x minus 2. And this is the last step, step 4. This is an inverse function, so I can write it with the inverse function notation, minus 2. And of course, to keep my denominator positive, my new x here cannot be equal to 2 over 7, or to keep my denominator from being equal to 0, to keep this function undefined. That is my new restriction on the variable x. Okay? So let's get into a little bit of graphing. Okay? So let's see what happens when we try to find the inverse of the standard quadratic function. So step 1, replace f of x with y. Step 2, interchange x and y, and then solve for y by applying the square root property. We obtain that y is equal to positive or negative x, which makes this not a function. Okay? So the plus or minus shows that for certain values of x, all positive real numbers, there are 2 values of y. Because this equation does not represent y as a function of x, the standard quadratic function, x squared, does not have an inverse function. And we can also see this with data. So if we look at the solutions of y is equal to x squared, if I square negative 2, I get 4. If I square negative 1, I get positive 1. If I square 1, I get 1. If I square 2, I get 4. This first row is the solutions. This is a function. All the x's are different. But when I switch x and y, if I like I would with an inverse, my x's now repeat, and my other x's repeat as well. So a function provides exactly one output for each input. Thus, the ordered pairs in the bottom, the inverse, if I were to change x and y, do not define a function. So we can tell in equations when things are not functions. We can tell in data when things are not functions. We also should be able to tell by looking at a graph. So if we look at the standard quadratic function, that's a parabola. If we draw a horizontal line, we can see that it intersects the graph at 2 points, it could be more, and that the set of these points will not define the function when their coordinates are reversed. The y's are different now. It is a function now. It passes the vertical line test. But when these 2 points are reversed, it will fail the vertical line test. So that's why we have something that called the horizontal line test. And what the horizontal line test lets us do is it lets us look at a function and see if the inverse of that function will also be a function. Okay? And then here's the formal definition for the horizontal line test. If a function f has an inverse that is a function, if there is no horizontal line that intersects the graph of the function f at more than 1 point. So if a function passes the horizontal line test, that means that that particular function will also have an inverse that is a function. So which of the following graphs represent functions that have inverse functions? Well, if we draw a horizontal line, as good as I can, we can see that A passes, B fails because it hits more than once, C fails, and D passes. Okay, so which of the following represents functions that have inverse functions? A and D, because both of those pass the horizontal line test. If we look at another one, B passes and C passes, A does not, because the absolute value function right here, while it is a function, the equation of this looks like that. It's a function, but it doesn't have an inverse that is a function. It has an inverse, but that inverse is not a function. Okay? So a function that passes the horizontal line test when no 2 different ordered pairs have the same second component. So this means that x1 does not equal x2, then f of x1 cannot equal f of x2 either. Such a function, if this happens, is called one-to-one. So basically, a one-to-one function is any function that passes the horizontal line test. It's a function in which no two different ordered pairs have the same second component. Only one-to-one functions have inverse functions. Only functions that pass the horizontal line test have inverses that are function. So let's talk a little bit about the graphs. Okay. So now that we know that in order for a function to have an inverse function, it has to pass the horizontal line test, let's talk about the relationship between the graph of a one-to-one function f and its inverse, f inverse. So because inverse functions have ordered pairs with the coordinates interchanged, if the point AB is on the graph of f, then the point BA is on the graph of f inverse. The points of A, B, and BA are symmetric with respect to the line y is equal to x. Thus, the graph of f inverse is a reflection of the graph of f about the line y is equal to x. And you can see that's true in this picture. As you see this line y is equal to x, the dotted line acts like the mirror, and these two functions are reflections of each other. Let's try it. Draw the graph of its inverse function. So I know that if there's a point 4, 2 on the graph, on the inverse function, there is the point 2, 4. X's and Y's get switched. Also, if the point -1, 0 is on the graph, the point 0, -1 is on the graph of the inverse. And the same thing for -3, 2. It would be -2, 3. And if I draw this graph, and I look at it carefully, I can see that if I were going to draw the line y is equal to x, that this graph, the black one, would be a reflection of the blue one over that line y is equal to x. Okay? So with this all in mind, let's finish by finding the inverse of f of x squared minus 1. But we already said that, well, first of all, this is the standard quadratic function, shifted down 1. Okay? So the graph, the normal quadratic function, if I graph this, it would look 4, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. So here's my standard quadratic function, shifted down, oh, whoops, shifted down 1 coordinate. And if I were to draw this, I could see that this fails the horizontal line test. Okay, there are multiple points where I can draw horizontal lines through this graph. Okay, so the standard quadratic formula does not pass the horizontal line test, but we're going to limit the domain. So if I limit the domain of this, now I'm only graphing the right side of this where x is greater than or equal to 0. So I don't need the other half, so now it actually passes. So let's find the inverse. So let's write this with y. And let's include this restriction right here that x is greater than or equal to 0. If I switch x and y, I also switch it in the restriction as well. Okay, let's solve for y. Add 1 to both sides. And then take the square root. So y is going to be equal to the square root of x plus 1. But normally, when we take the square root of both sides of an equation, we need to include the plus or minus, which would make this not a function. But in this case, y is greater than or equal to 0, which means I don't need the negative, which means I only need the principal root, which means this is a function since y is greater than or equal to 0. So now when I graph my inverse function, which is the standard square root equation, shifted left 1, you can see that these two graphs, even though they're not very nice, that these two graphs are reflections of each other across the line y is equal to x. And that is 1.8 inverse functions.